Hi, this is Dr. Rajesh Kumar, and let me now sort of jump into the discussion topic for today, which is a tutorial on K nearest neighbors or KNN. Okay, so what would be the agenda? Basically, we will go through what is machine learning, what is the KNN algorithm or K nearest neighbor algorithm, how does it work, and then we will look at the use cases where you can apply this KNN algorithm. And then we will look at couple of hands-on examples, or basically, we will run some code in Python to actually implement KNN and look at couple of results. And we will look at in the end, some references as well, which is some books that you can refer to if you want to learn more about KNN. Okay, so let's get started here and talk about machine learning. So machine learning actually is nothing but it is a subset of artificial intelligence, which provides machines the ability to learn automatically and improve from experience. So what does this mean? Actually, artificial intelligence is nothing but being imparting intelligence like human beings to machines. So if you think about human beings, we can understand language, we can be creative in terms of drawing, etc. We can learn from our history and so on. So when we try to impart these kinds of skills to machines, then that is called as artificial intelligence. And then within this, there is one topic which we just mentioned, which is of machine learning, which is how can machines learn from history or from experience like we learn as human beings from our history or from our experience. So let's say, just to take a couple of examples, if I have a history of failures of a particular machine, so in petrochemicals, for example, there can be compressors and pumps and so on. And if we have historical failure data of these machines, based on this failure data and some of the root causes, etc., can we predict in the future when a failure will happen so that we can prevent it? Or let's take an example from supply chain, because now during coronavirus, supply chains are facing a lot of issues, right? So let's say that, can we predict when shortage of particular parts will happen? Or from a commodities perspective, if you are a car manufacturing company, right, and you procure certain, let's say, steel or plastic or whatever in large quantities, you would like to know what is the price of plastic or steel, or what will be the price in the future. So if the price is going to decrease in the future, then you would like to postpone your buying, right? Whereas if the price is going to increase in the future and you know that today, then you would rather buy it and keep it in your inventory so that you don't have to pay a higher price in the future. And for this, you will need to predict the price in the future, right? Based on maybe, let's say, historical data and the root causes which contribute to price of commodities. So these are some of the examples of real life examples of machine learning. And what we do here is basically we continuously feed data and try to predict the future. Okay, so now machine learning is not just of one kind, right? There are several kinds of machine learning. So the first one is what is called as the supervised learning. As the name suggests, right, it's called supervised, which means that basically we tell the machine or we tell the algorithm that from the historical data, which data set belongs to which class. When we say class, what we mean is, for example, in the predictive maintenance case that we talked about, which is, you are trying to predict, let's say, when a machine is going to fail, right? So there can be two states. One state is that the machine has failed. Another state is that the machine has not failed, right? And from the historical data, if we can associate each instance with the state that whether it has failed or not failed, then that is what is called as supervised machine learning. So which means that you are already telling the machine in the history, well, this class belongs to the failed state and the other class belongs to non-failed state. So that's supervised. So then obviously there is another class which is called unsupervised machine learning. which is where typically used when you are not clear about what you want to do with the data, right? So you are just trying to explore the data. You don't know what classes are there in the data. Like we said, right? There is, like, for example, in the previous example, we had the failed state and the non-failed state, right? But in the unsupervised machine learning, we don't know these states. So let's say, what is the example of unsupervised machine learning? And typically, most of the customer segmentation or customer profiling or clustering is an example of unsupervised machine learning. So to give you a real life example, we are working with a utility company in Japan, which provides, water, electricity, and gas to the houses in and around Tokyo. A large company with almost 10 million customer base, and they were collecting data from smart meters on, what is the electricity, gas, or water consumption every, in electricity case every 6 seconds, and in the water and gas case, let's say every, couple of minutes, or every hour, right? And what they wanted to do was to be able to profile the customers, that, when do a group of customers, let's say, sleep or wake up, or how many times do they cook. So from the smart meter data, actually we can find out whether you are cooking or not, or whether you are taking bath, how many times do you take bath, etc. Do you take vacations, how many times do you take vacations, and so on. And the reason why they wanted to do this was basically they would like to segment their customers, that, okay, these group of customers, they probably take more vacations, right? So then they would like to partner with third party companies to provide some services, like, for example, maybe insurance services. And if you, for example, eat out a lot and don't cook much at home, then maybe provide, a tie up with some restaurants for food delivery, etc. So that's an example of unsupervised machine learning, where you do not know what kind of customer classes you have, but you would like to find that out from the, and let the data tell you that, okay, this is the group of customers which probably takes more vacations or takes less vacations, etc. Okay, so that's an example of unsupervised learning. And then let's talk about another class, which is called as reinforcement machine learning. And typically, in some cases, actually what happens is that you may not have enough, data from history, but you would actually like the machine or the agent, as we call in this particular case, to learn from the actual actions that are being taken, and whether that action takes you towards the goal or away from the goal. So for example, if the action takes you towards the goal, then you get a reward. And if the action takes you away from the goal, then maybe you get a penalty, right? And can you learn from this kind of interactive data, right? So basically, you in reinforcement learning, you have an agent, you have the state in which your system is, and then you have an action. Basically, an action can be like, if you are playing chess, then maybe making a move, and then an associated reward or penalty, depending on whether you actually win or whether you lose, or you move towards the goal or away from the goal. And this is akin to something like when you are trying to train a dog, right? Which is like, okay, every time I ring a bell, you should stand up. And every time the dog stands up, you give it a biscuit, right? And then it learns that, okay, every time there is a bell ringing, I need to get up, right? And I'll get a biscuit. And every time, it doesn't get up, it doesn't get a biscuit, right? So that's sort of, penalty or whatever, right? So this is an example of reinforcement machine learning. And in real life use case, how we use it is, for example, we have used it in a project for adaptive pricing, like, for when we are pricing for products for a company, and that pricing becomes stale, right? It becomes stale after a period of time. And therefore, what you would like to do is basically keep that price changing or dynamic in such a way that if your revenues are falling, you would like to reduce the price. And if your revenues are increasing and maybe there is a lot of demand in the market, you would like to actually raise the price, right? And you may want to actually have a machine learn this thing instead of maybe having some human actually take the decisions, because it might be very slow, right? So you could use reinforcement machine learning actually to do this adaptive pricing kind of a thing. Okay, so that's an example of reinforcement machine learning. And the case that we are discussing today is basically the KNN algorithm, which is an algorithm which we used for mostly supervised machine learning, which is where you have labeled data. Okay, so what is KNN algorithm? So as we said, KNN algorithm is K nearest neighbors algorithm, and it is an example of supervised learning algorithm where basically you try to classify a new data point based on the neighbors of that data point, which is basically which data points are closer to it. For example, here as you can see, you have on one side couple of cats, and on the other side you have couple of, on one side you have dogs, and on the other side you have cats, right? Now if a new data point is given to us, there is a picture of a new animal, and if it is lying somewhere here, right, then we know that it is nearer to the cats, right, and therefore we will classify it as cat. Whereas if it is sort of nearer to the dogs, then we classify it as dog, right? So that's the, like, neighborhood for the dog, and therefore we sort of classify it, that new animal or the new picture, as being or that of a dog. And this is quite this is something which is we even see in our regular day-to-day life, right? We have had examples where our parents keep telling us, okay, don't play with those kinds of children or something, because they are not good in their studies, or probably they are not so good in their behavior, because you would become like them, right? So it's again an example from real life of classifying a particular person based on the company that they keep, right, or from the with the kind of people that they are. So that's sort of the example. And now let me actually go back. Okay, what are the features of k nearest neighbors algorithm? Okay, so let's talk about the features of KNN. So as I said, KNN is a supervised learning algorithm. Typically, it is used for supervised learning kind of problems. It's very simple, as we mentioned. Intuitively, you can it's about what kind of neighbors do you have. So your class is predicted based on the your nearest neighbors, as the name suggests. And then it's a non-parametric technique. So I would like to spend a couple of minutes here to discuss about what we mean by non-parametric. So typically, the supervised machine learning algorithms are of two kinds, right? One is the parametric types, and the second one is the non-parametric type. When we say parametric, what we mean is basically that the machine or the algorithm assumes that there is an underlying function or a distribution that is known of the particular data set. Like, for example, the linear regression would assume that the relationship between two things x and y is linear in nature, right? um, and similarly, for a distribution, a Gaussian distribution, it would assume a normal distribution of the data points, and so on. So a lot of the supervised machine learning algorithms, they assume some kind of function association between the predictor, which is basically the root causes which help you in predicting, and the variable that you are trying to predict. Whereas there are certain algorithms like the KNN or the Parson window or the linear discriminant analysis, which is of the kind which is called non-parametric, because it does not assume any particular kind of distribution or any particular kind of functional relationship of the data that you are trying to predict, or you're trying to learn the pattern of. So KNN is one of the kind, as I said. Parson window is another one, which is basically where you in Parson window, essentially the volume of the data set, or the area that the data set covers is known, whereas you're trying to find the k there, which is the number of data points within that area or the volume, right? Whereas in case of non-parametric technique like KNN, it's the opposite, where the k is known, which is basically you would like to associate the class of the data point that you are trying to predict based on the k number of neighbors around it. Now k can be 3, 4, 5, whatever, right? 10, 20, and so on. Essentially, the difference between parser window and KNN is that in KNN you already know the k, and then from the k you try to find out the volume, and therefore then you try to find the probability or the density underlying distribution. And then there is the discriminant analysis, which is of again two kinds: linear discriminant and multiple discriminant analysis, where basically what you do is you transform the underlying data, the features, into a higher dimension, and in such a way that in the new feature space, after you have transformed the data, you now try to apply a parametric approach. Like for example, you will try to project the features onto a line, or if it is on a subspace which is higher dimension than a line, then essentially it becomes multiple discriminant analysis. So basically, those are the three kinds of non-parametric techniques. So even if you were not able to sort of get the full hang of what these three types are, what you need to keep in mind is that non-parametric technique does not assume any kind of distribution or any kind of functional relationship of the underlying data, and therefore it gives us a lot of flexibility. Whereas the parametric techniques, they basically assume some kind of functional relationship between the data points, or they assume some kind of distribution. So where would you use a non-parametric versus a parametric technique, right? So basically you would use non-parametric technique, where you do not know about the functional relationship. That is one. Second is that there is maybe, let's say, large amount of data and so on. And thirdly, non-parametric technique like KNN does not work in a very high dimensional data. So you would also use parametric techniques in that case. Whereas if you have smaller data sets, you would use typically non-parametric techniques. And then also, if you understand that the relationship between the data points might be, for example, linear or something like that, you would use a parametric technique. So you are assuming that there is some kind of relationship, like a linear relationship or something like that between the data point. So that's where you will use the parametric technique. So again, just to summarize, basically non-parametric is an approach where you do not assume any kind of distribution or functional relationship, whereas parametric assumes a functional relationship or basically a distribution between the data points. The other feature of KNN is that it is a lazy algorithm. So what do we mean by lazy algorithm? Actually, in most of the supervised learning algorithms, you basically train your model on the training data set, then you have your model, and then you apply this particular model to the test data set to then classify or predict, for example, whether a new image is that of a cat or a dog, right? So this can be, some kind of algorithm like support vector machine or regression or logistic regression or whatever, right? So you run this logistic regression or you run this regression or support vector machine on the training data set, and it learns the features or it learns the parameters of the model from that data set, and then applies this learned model on the test data set. Whereas in case of KNN, actually there is no training step at all. That's why it's called a lazy algorithm, because what it does is, at the time that you are actually now want to predict, at that point in time, actually it will go and it will do all the calculations of the distance of the new data point, like for example the new image of the cat or dog, from all the other data points that you have. So it will calculate all the distances, and then we'll check for those data points which are, or the k data points which are nearest to this. So that's why it's called lazy algorithm, because nothing happens till the point, or no calculations happen till the point you are actually trying to predict something. So there is no training step involved. Okay, and then it's used for both classification and regression, as we just mentioned. So it can be used to predict the values as well as be able to classify something like, okay, whether it is a cat or dog, or if you're trying to, let's say, predict some value, some forecast or something, that for that also you can use it. And then it is based on feature similarity, which is basically, what do we mean by feature similarity? So feature can be things like, if for example, you are looking at classifying cats versus dog, right? So is the eyes like a dog? That can be one of the features. How do the ears look? That can be one of the features. What about the tongue, the face, and so on? So there can be multiple such features, and how similar these features are between two data points, which is used basically by the KNN algorithm. And then, as I said, there is no training step involved. So these are the features of KNN algorithm. And therefore, now let's look at actually just some simple examples of how it works. So as you can see here in this slide, we have two classes of data. So one is all these blue data points, and there is another one which is the orange data points. Now, if you have a new data point, which is this pink one here, which class should it belong to? Should it belong to class A or should it belong to class B? So what you would do is you would actually start calculating the distance of this pink data point from every square or blue triangle data point. And then you will decide, you will have to assume a particular K. Let's say K is 3, right? Which is, I'm looking at the nearest 3 data points. And in that case, basically, as you can see, if we draw this circle, right, then we see that 2 of the nearest data points within that circle is of the square orange kind. So basically, we will predict that this particular new data point belongs to class A. Whereas K value was 7, right, as in this particular example now. You would see that 4 out of the 7 is actually of the blue triangle kind, and therefore we will now classify it as belonging to class B. So essentially, this prediction changes, as you can see here, depending on what is the K value. So therefore, the question is, what should be the value of K, right? And typically what happens is you run a trial and error, and basically you come up with, okay, what is the best K value? But essentially what one needs to understand is that as the value of K increases, basically the partition line starts moving towards becoming more and more linear. So it starts becoming less flexible, and it starts assuming some kind of a linear dividing line or something like that. So what happens is that in that, as you increase the K, your bias basically increases, but your variation reduces. So we know that in classification problems or in machine learning problems, bias and variance are two things that we are trying to manage, right? Bias is basically how close you are to the actual class, or to the actual value, whereas variation is how much variability is there in your prediction. So as the K increases, the bias sort of increases, but the variance reduces. And then it is vice versa. So if your K decreases, let's say at K is equal to 1, where you are only looking at just one nearest neighbor and then predicting based on that, actually the bias is the least, which means it is the most flexible. K is equal to 1 will give you the most flexible demarcating line or function, whereas the variability will be the maximum. So that's the sort of the trade-off. And that's how we actually determine K. So we have to get a K value in such a way based on trial and error that sort of maximizes our or reduces the bias as well as the variance, and that's the kind of optimization we are trying to do. Okay, so how do we calculate the distance itself, right? And distance typically can be of many kinds. So the example here is of the Euclidean distance, but you can have other kinds of distances like Manhattan distance or Mahalanobis distance, and you can look up references for other kinds of distances. Now Euclidean distance is calculated for the point P1 and P2 as given here. Essentially Euclidean distance is nothing but the square root of sum of the x coordinates of these 2 points P1 and P2, and then y coordinate square of these 2 points P1 and P2. And this is just an example of one kind of distance, and other kinds of distances like Manhattan or Mahalanobis are also there. And then this calculating this distance becomes quite challenging, especially in cases where you are trying to, for example, calculate, let's say, how close two LinkedIn profiles are, right? Or trying to classify the category of electrocardiogram and so on and so forth. So there we have to bring in more creativity to just decide what kind of distance to use. Okay, now let's move ahead. We will now talk of some use cases where KNN can be used, and this is an example of how KNN can be used for book recommendation. So if you have purchased books on Amazon or wherever, right, some of these recommendations are based on KNN algorithm. And then as we said, KNN is like based on features, right? So maybe let's say what will be the nearest neighbors of a particular book. It can be based on who is the author, what is the topic, and so on and so forth. And then there are other use cases like I mentioned, so for classifying satellite images, for classifying handwritten digits on image analytics, or for classifying electrocardiograms, etc. Typically KNN can be used. Okay, so now actually we will get into some hands-on. Okay, so to start the hands-on session, I'll go to this Jupyter notebook that I already have installed on my system, and I have a certain code written which we will take two examples. Both the examples are based on data sets which are available in the open source, so you can easily get access to that data. So what we do is we start by importing the necessary libraries. So we import pandas, Seaborn, NumPy, and Matplotlib. Basically, pandas and NumPy are there for doing the data manipulation and also for storing data as matrices or as arrays, and be able to perform some mathematical procedures on them. And then Seaborn is basically used for plotting, and Matplotlib for plotting as well. And this line here, get IPython, just helps us to run the images that we'll be creating in line with Jupyter Notebook instead of opening up a new window. So let's run this. And what it will do is it will import all these packages for us, which we are going to use. And then we will first import the breast cancer data that is available in your scikit-learn datasets. So we import that, and then let's just initialize that data into a variable here called cancer. So cancer here represents all the load, the breast cancer data. And now let's actually look at what this data is. It's a bunch of attributes in this dictionary here. So you have data, the target, which is basically nothing but whether it is a cancer or not. So whether it is malignant or benign. Malignant means it's a bad cancer, and benign means, well, it's just a tumor, it's not cancerous. Target's name, description, feature names, which is basically the features that will tell us whether a particular case belongs to cancerous or non-cancer, or malignant or benign. And then actually let's just print the description of this particular data here. So as you can see, we can use this command to print the description here. And then we see that there are 569 data points with about 30 attributes. And these attributes are radius, texture, parameter, etc. And the max and min values of those are given here. And then now let's look at some of the feature names. So these are the feature names, radius, texture, and so on. And now let's actually set up a data frame of this particular data here using pandas, this function here. So there are 569 data points, and all these are basically your features as we talked about. And let's look at the target variable, which is nothing but whether it is telling us whether a particular data point belongs to malignant or benign. So 0 is cancerous and 1 is non-cancerous. And then we convert the target into a data frame as well. And then let's look at the couple of examples of how the data points look like. This is one row of the data points which with all the several feature values that we have. So basically we use this package called standard scalar from scikit-learn for pre-processing and for standardizing the variables. And we initialize this standard scalar into a variable called scalar. So standardizing is nothing but basically bringing all the samples to essentially the same range, right? Because what might happen is some of the data point, like for example temperature might be from 0 to 100, and some price might be from, let's say, 1,000 to 100,000 or whatever, right? So the absolute values can lead to some issues with respect to the prediction. Therefore we have to standardize it or bring it between, let's say, -1 and 1, so, and then a mean of 0, right? So we have to bring everything to the same scale to be able to compare the samples. So we first of all we fit this standardization or normalization on the data set we have, and that is we calculate the variance and the means, and then we actually apply it on the data set to transform it to the actual values. And then if we look at the scaled values now, so let's look at the scaled values, and this will give an example of the top 5 rows here. So we can see now the values are between -1 and 1, or rather it is standardized essentially with a normal distribution. And then we divide this data into test and train. So basically we will train the model and then we will test it on a separate data set. If you use the same random state, you should be able to get the same result. Otherwise you may get a different result here. And essentially we are keeping the testing size to 30, which means that we are dividing the entire data set into 2 parts: the train part, which is having 70% of the data, and the test part, which is having 30% of the data. And again we are using this package called train test split from the scikit-learn package. So we get the x and the y's, which are basically nothing but your train, and the x's are your predictors and y is your predicted variable, whether it is cancerous or not. And then now let's import the k nearest neighbors classifier. This is the actual algorithm which we are importing from scikit-learn package. And now we initialize this particular algorithm, and then we fit it on the data. And some of the parameters, as you can see, is basically what is the leaf size and so on and so forth. The nearest n neighbors we are taking. So we are taking k is equal to 1 here, basically, as of now. We will see the results based on that, and then we will change it and see how the results vary. And we now run it on we now try to predict it. And then we will now try to evaluate what the results look like. So we have imported the classification report and confusion matrix, which is basically trying to see whether we were able to correctly classify the cancerous as cancerous and non-cancerous as non-cancerous as or not. So we can see that this is the actual and this is the predicted. So basically some data points here, 5 and 4, are classified wrongly. Otherwise all the others are classified well. So if we look at the accuracy, calculated accuracy actually, so we see that the precision, which is true alarm, right, which is basically from the cancerous samples, how many were you able to actually predict as cancerous. So if you see, the accuracy is quite high, almost 94-95%. And then the recall, which is from all of the cancerous samples, how many were you able to actually predict accurately, is about, again, 94-95%. And F1 score is nothing but a combination of both precision as well as recall, and that's quite good as well. So with k is equal to 1, we are able to get already some good results. Now let's try to see how to choose the k value, right? So this is basically nothing but a bunch of code that actually runs the k value from 1 to 40 and then tries to check the accuracy. And this is just like doing a trial and error to see where we get the best results so that we can then use the best k value. So if you can see this particular plot here, after we plot the result from the running the trial and error from 1 to 40, we see that the error actually starts decreasing, and somewhere around this k is equal to 21 we get the minimum value of error. So for us the best k value is 21. So now if we compare the results between k is equal to 1 and k is equal to 21, we should be able to see the prediction result. So as you can say, this was the result with k is equal to 1, which is we get about 94-95% accuracy. And then with k is equal to 21, we will see whether the accuracy improves, right? So we see that yes, the accuracy has now gone up to almost 99%, which is, we earlier had 9 misclassified data points out of all of the points, and then here we have just 2 data points which are misclassified from the test data set. So now this was one example of applying KNN on the cancer data set, which is available freely. And now let's look at another example, which is the iris data set, and again available freely as well. So iris is a type of flower, and we will see what flower is it. So just give me a moment here. So we again start by importing the necessary libraries, and then we'll look at what this iris dataset is. So the iris dataset comprises of 50 samples of 3 species of iris flower, which is iris setosa, iris virginica, and iris versicolor. These are the 3 types of iris flowers. And if you run this, basically we will find that, okay, sorry, we did not copy the entire the code here, so it was giving an issue. Let's just run it again. Okay, so we see that it is this particular flower, which is iris setosa. So the iris setosa you can see. And now let's look at the other 2 kinds of flowers here. So which is iris versicolor. So this is iris versicolor. And then you have the iris virginica. So we see that this one is iris virginica. So essentially we now will import the sort of data set. We have already done that, and we will now use the Seaborn package to actually plot some of this data and see how it looks like, which is basically do some kind of exploratory data analysis. So if we look at the data itself, so this is the top 5 rows from the data, right? So essentially the data consists of basically what is the sepal length, sepal width, petal length, and petal width. And this is nothing but basically your petal is your this colored part of the flower, and the sepal is basically your green part here, right? So it is talking about what is the sepal length, sepal width, and petal width of each of the species, whether it is setosa, virginica, or versicolor. And we will see whether we can use KNN to actually classify these flowers into the data points into these categories of flowers. So let's do some quick exploratory data analysis on this. So we are running a pair plot on the data set, and in the meantime I'll just copy another part of the code here. Okay, so now the plot has come up. So as we can see that the green is basically your setosa flower, and we can see that this pair plot actually just plots the sepal length, sepal width, and the petal and petal width of each of the samples of setosa, versicolor, and virginica. And we see that the green dots, which are the setosa flower, is actually quite separable from the others. It's when you plot, let's say for example, sepal length and petal length, right? We see that this is quite separate from the other data points. So let's see whether we can actually be able to classify it using KNN or not. And here we are running a kernel density estimation function on the setosa flower to check what kind of distribution it has. So this is the kernel density estimation plot using the SNS package. So only for the setosa flower. So if we plot the sepal length and sepal width, we get something distribution like this. So essentially we see that the maximum centered around here, and then there is a distribution as you can see here. So there's some kind of a linear relationship here. Okay, so now we will again do the same standardization of the variables that we had done in the cancer dataset case. So we are importing the standard scalar function from the scikit-learn preprocessing. So we will initialize that. So we are again basically doing the standardization or normalization of the data. And we will do the standardization on everything except the species, which is a categorical value, right? So it's categorical whether it is which kind of flower it is. So we have removed that, and then we have done the standardization or normalization on rest of the data. So we now convert this into a data frame, a pandas data frame. And if we look at the top 5 rows, now it's all converted or transformed. So the values are now normally distributed basically. Okay, so now we divide the data again into train and test. And we again have a training of about 70% and test data set of about 30%. So we are dividing that entire data set into these 2 buckets. And we will now use KNN to see if we can use KNN to classify them. Again, the same n k is equal to 1, and we will check the results, and then we will do a trial and error to check what is the best value of k. So here k is equal to 1, and now we are going to predict on the test data set and look at the results. So we are now importing the classification report and the confusion matrix. So if we look at the confusion matrix, we see that kind of already we are getting quite good prediction. So just 2 misclassified points. And if we look at the accuracy, we see that the accuracy is quite high, around 96% already. Now we have to see what is the best value of k. So essentially we will again run k is equal to 1 to 40 and check which is the best value. So let's plot the errors when we vary the k from 1 to 40, and we see that actually the error decreases and then increases. So basically the error is minimum with k is equal to, let's say, 3 or even 5 or maybe 11. So let's choose one of these values. So let's say k is equal to 3, and let's see how the results look like. Does it improve the accuracy or not? So we now see that even the 2 data points which were misclassified earlier is now classified properly. So the accuracy improves to 100%. So that's the example of how you can choose k. So we have covered the hands-on, and now we will look at some of the references. So some of the references are basically these 3 textbooks here, which I found quite good. Some of them are even available online, so you can refer to them if you want to learn more about KNN. And also they are quite good references for some of the other techniques as well. So that's all I had to share. So thank you